Hello everyone, welcome back to CPE 517-WS Digital and Computer System Architecture course. This is part 6 of lecture 4, long execution cycle, instructions and exception. Okay, so believe it or not, we have to be clear that the 5-stage pipeline assumes the 5 stages like instruction fetch, instruction decoding, execution, memory, and write back. 5 of them have the same latency, right? See here. So we assume register, write back, memory access, execution, instruction decoding, instruction fetch has the same latency, because once you finish execution, when you go to memory access, you also can do write back, you also can do execution, you also can do instruction decoding and probably instruction fetch. So this is one of the important assumptions that the 5-stage pipeline can always deliver one instruction at a time, because every function unit takes one cycle, right? But unfortunately, different instruction stages actually takes different amount of cycles. For instance, instruction fetch, instruction decoding, memory access, write back typically I'm saying takes one cycle, but execution takes extra cycles. Like execution of integer unit takes no extra cycle, but the floating point, addition, multiplication, division, or integer multiplication, integer division takes extra cycles of 3 cycles, 6 cycles, 24 cycles. Okay. This actually is very obvious because, for example, if you do floating point operation, you always have to first derive the value from the floating point and then do computation for the different parts of the floating point, and then transform that back, right, to the real value of the floating point. So that's why it takes slightly longer time than, let's say, integer-based execution or instruction fetch, instruction decoding, memory access, and write back. So given that in our mind, so what we can see here is like this, shown in this slide. You have one cycle of instruction fetch, one cycle of instruction decoding, and one cycle of integer unit execution, but 7 cycles for integer or floating point multiplication, 4 cycles for adder, floating point adder, and a lot more for floating point or integer division. And then it's memory access right back. Okay, given that knowledge in your mind, do you guys mind finish using 15 minutes to finish this 5-stage pipeline, considering multiplication takes 7 cycles, addition takes 4 cycles, and also consider the hazards. For instance, the load of F4 is actually data dependency for multiplication, right? And then addition, multiplication depends on multiplication, store depends on addition. And when you have those kind of data dependencies, you also want to understand there could be some structure dependencies. Okay. Please pause the video for 15 minutes or 20 minutes, try to solve this, and then we move on. Okay, so hope you get some a taste about how it works. And let me show you the correct results and explain why it is like that. Okay, so first you have the first instruction fetch, decoding, execution, memory access, write back. For the second instruction, because it's a multiplication, right, then you're gonna have your 7 cycles of multiplication. But however, when it goes to instruction decoding, you have to have a stall because the load delivers the results at the end of the memory access. So there's one stall here, and then you have 7 modification, memory access, and write back. This actually introduces more complications. So when it goes to addition, you have instruction fetch, and then you have a stall. Why? Because of the structure hazard. Because only one instruction can occupy the instruction decoding, right? See here. This instruction is a holding instruction decoding function unit for cycle 3 and cycle 4. Then the third instruction, the addition instruction, can only start using instruction decoding at the 5th cycle. So that's the structure-based stall. And then when you want to add F0 and F8 to F2, the instruction decoding has to wait until even we have the write back, the data forwarding. So the results of F0 should be finished at the end of multiply, right? So you have to have the stall until cycle 12. This is data stall, data hazard. So you have the addition, 4 additions, memory access, and write back. Okay, so you can see for the third instruction, you have both structure hazard and data hazard, right? And this is gonna make it more complicated for the fourth instruction. See here. We cannot issue instruction fetch here because instruction fetch, this function unit is occupied by the addition instruction until the end of cycle 4. So we can only issue this instruction at the fourth store instruction at the beginning of instruction cycle 5. Okay, and then you have quite a bit of stalls because the instruction decoding is occupied by addition instruction from cycle 5 until cycle 11. So you can only do instruction decoding after cycle 11. It's here. So that's a structure hazard. This is what's a structure hazard. Okay. Okay, when it goes to the store instruction, you have the stall before the instruction fetch. So that's why you cannot have the instruction fetch here because addition is occupying instruction fetch. Only after addition release this instruction fetch component, it goes to store here. Okay, then the store instruction have the instruction fetch, and then it has a lot of structure hazard because of instruction decoding until the release at cycle 11. So we have the instruction decoding here for store instruction and execution. The execution of store instruction calculates the address here. And then before we do the store of this F2, we first have data hazard because we have to access this, and then it goes to function memory, function unit occupation of memory. So even we can issue memory access here, but because the addition is first, right? So it occupies the memory components here at cycle 16. So we say from cycle 14 to 15 is the data hazard, and cycle 16 is the structure hazard. It goes to the store at the end of cycle 17. This is actually a very classical and representative type of problem for this hazard non-instruction, like data hazard, structure hazard, and non-instruction data dependency 5-stage pipeline. Okay. Okay, so now goes to exception and interrupt problems with pipeline. Imagine you are doing pipeline, right? So what if in the middle of some instructions, you had an exception or an interrupt? So that could be a problem because it might don't know when to report it because some of the instructions are already happening, right? So the exception formally is defined as an unusual event happens to an instruction during its execution, such as divide by 0 and define opcode. Interrupt is the hardware signal to switch the processor to a new instruction stream. For instance, when I was talking to you, I'm using Zoom for recording. So the process is doing Zoom, assuming it's a uniprocessor. And then I'm also moving the mouse, right? And I also have the monitor, have the camera. So it means
whenever I move the mouse once, I'm gonna send an interrupt, okay, to the processor. The processor has to be broken from the zoom and then handle my interrupt first, because this kind of peripheral devices signal has higher priority comparing to the process. And in this example, we use the sound card interrupts. When it needs more audio output samples, it's gonna typically send an interrupt to the processor. So whatever was working, gonna have to wait until this interrupt to be served. The problem is it must appear like that the exception or the interrupt must appear between two instructions. Then the effect of the word instructions up to and including instruction I is totally complete. And no effect of any instruction after instruction I can take place. So it's like, even we're doing pipeline, but the effect, well, it looks like the instruction is executed one instruction finished at a time. That's very important. The exception or interrupt handler either aborts the program or restarts the program at instruction I+1. Even probably some of the part of I+1, I+2, because of the 5-stage pipeline, some part of it, like instruction fetch, instruction decoding, are already finished. But we're gonna abort all the executions after instruction I. So only appears like whatever before instruction I are finished, totally finished, complete. Well, whatever after instruction I, seems like nothing happened. So that has to be preserved. Okay. So this is the 5-stage pipeline. You have the PC of instruction fetch, instruction decoding, right? Execution, memory access, and write back. So you could have cases like we kill the instruction at a stage instruction fetch, or kill it instruction decoding, instruction execution, or anomalous interrupt. So the key observation is architect state only change in memory and register when write stages happens. So only when the memory commit happens, the commit point. Before that, whatever happened, it does not affect anything. So we can allow them to happen until the commit, which is a write back or loading the memory or storing the memory. So whatever instruction fetch, instruction decoding, execution are totally fine. You can go ahead, do it. But when it goes to commit point, we're gonna have to be very careful if you have exception or interrupt, okay? Well, this is a table summarizing the possible exceptions, like instruction fetch, you have a page fault on instruction fetch, like whatever instruction you are fetching, it might not appear in memory. Or misaligned memory access or memory protection violation. This is very similar to memory access because it's the same as memory accessing memory. ID, like instruction, undefined or illegal opcode. Execution, arithmetic exceptions like divide by 0. Write back typically does not have any exceptions. This table summarizes the possible interrupts. Interrupts is mainly about peripheral devices like IO device request, vector interrupt, invoking OS from a user program, tracking instruction, excepting like standard IO printf is invoking the operating system print from user program, right? Breakpoint, integer arithmetic overflow or underflow by floating point trap. Page fault, memory protection violation, undefined instruction, power failure. So these are pretty much like either peripheral devices or something that requires the operating system to involve in order to solve this problem, right? Okay, so to summarize the talk, we have in lecture 4, we have talked about 5-stage pipeline, 3 hazards, branch schemes, floating point operations, exception, and interrupts. All right. So homework, we're going to require you to finish homework on appendix 8.1 due time and question and syllabus are all going to be shown in Canvas. If you have any questions, please let us know. I'm going to also announce this in the announcement of the Canvas.